If we consider an electron in an electromagnetic field, we can write down an invariant Lagrangian. I have already described this Lagrangian also in other videos, other courses, for example in the course called Covariant Formulation of Classical Electrodynamics, but it suffices to say that we just search for some invariants. And in special relativity, we have the following invariants. So I'm going to consider a minus sign, the mass of the electron times the speed of light squared, which I can also rewrite using tensors, dx mu over d tau, which is proper time, tau is proper time, era mu nu, the metric tensor, and then I have dx nu d tau. So this quantity here is simply the speed of light squared, because we also know that the invariant element ds squared is dx mu era mu nu dx nu. So this is the invariant length squared, which is also equal to c squared d tau squared. And therefore, this is why this is equal to c squared. But we don't need it now. So this is the first invariant that we consider in special relativity. And then when we have an electromagnetic field, there is another invariant. And in particular, it's a term of this kind. So in general, I have a minus sign, but this is actually a choice. It doesn't really matter. This would influence let's say it would affect the equations, the Maxwell's equations, some of the Maxwell's equations. They will depend on this vector a mu. This is a four vector which contains the potential A0 and the magnetic potential AI. So the first component is A0, and then we have AI, which is A1, A2, A3, and this represents the magnetic potential. A0 might be a potential, it may also not be a potential, but this is only, let's say, related to the electric field. So A0 only appears in the expression for the electric field. And if the field is electrostatic, then this would be a potential. But anyway, let's move on. Here I have A mu, and then I have dx mu d tau. So we'll contract this tensor with another tensor, which is the force velocity, and then I multiply by some constants, which are the electric charge q divided by the speed of light c. So this is some kind of an invariant Lagrangian. And the metric era mu nu in this case is selected to be 1 minus 1 minus 1 minus 1 on the diagonal, and then I have zeros outside of the diagonal. And d tau in special relativity is the square root of 1 minus v squared over c squared dt. T is the time measured in a frame which is quote unquote still, whereas tau is measured in a moving frame. So the frame where I measure tau is moving with respect to the frame where I measure t. And the time that elapses in the moving frame is, let's say, smaller, or it's passing more slowly than the time that elapses in the non-moving frame, which is this one. You can see that this quantity here is less than 1. And then what I have to do basically is I have to take the variation of an action, so it's an integral of the Lagrangian over d tau in this case, because I want to find invariance. So I integrate over d tau, and I have to set this equal to 0. But I can also rewrite it in this fashion, in particular the variation of, in this case I want to rewrite the Lagrangian as a function of the coordinate x, the coordinates x, y, z, and t, or x1, x2, x3, and t will be x0. It will be related to x0. And I simply have to rewrite this expression above and it's quite easy to see that I can write it like this: minus m c squared, and then I have the square root of 1 minus v squared over c squared, and then I have plus. So I'm rewriting this like this because, as I said, this is just equal to c squared. And then I have d tau in the integral, which can be rewritten using this expression. So I can put the square root here. And then I have plus e a0. So I'm using e, and I have simply defined e to be minus q. So q is equal to minus e. And in this case, e will be positive because we are considering an electron. So q will be negative, but e will be positive. EA0 divided by the square root of 1 minus v squared over c squared, and this factor appears simply because I have d tau in this expression. So dx mu is composed by dx0 d tau and the vector dx d tau. So this first part can be simply written like this. So dx0 will be c times dt, and then I divide by d tau. But this will be c divided by the square root of 1 minus v squared over c squared, and this factor of c will simply cancel this factor of c here in the denominator. So I have EA0 over the square root of 1 minus v squared over c squared, but I also have to remember that I have to multiply by the square root of 1 minus v squared over c squared, which comes from differential inside the integral, so this differential here, and therefore that differential there. And then I have minus a vector divided by the square root of 1 minus v squared over c squared times e over c. And in this case here, I have a minus sign because of this. So let me do it here. So this part comes from the fact that I have x dot I era ij aj. I can rewrite it like this, right? Because this is equal to x dot I ai, but this will be minus x dot product a, like this. So I have to take the dot product with the velocity that I can call x dot or v. So let me put the dot product here. I have dot product v, and v is simply equal to x dot. This is equal to the velocity v. And then I multiply this by the square root of 1 minus v squared over c squared, integrate over dt. So some of these factors will cancel. This one, this one, this one, this one, and this can be set equal to 0. And this is exactly the Lagrangian that we usually have in classical physics, classical non-relativistic physics. And if I want to find momentum, p, I have to take the derivative of the Lagrangian L with respect to the velocity v. And from the expression above, I will simply obtain mv over the square root of 1 minus v squared over c squared, which is the derivative of this expression. And then I will have minus a e over c. This is just the other part. For small velocities, this will be approximately equal to mv minus a e over c, because this factor of this part of the expression will be approximately equal to 1. This is true for the absolute value of v much smaller than c. And then I can find the Hamiltonian. So the Hamiltonian can be written in this form: derivative of the Lagrangian with respect to the velocity, dot product with the velocity minus the Lagrangian. And this is equal to mv squared. Let me write it like this. This is the magnitude squared of the velocity minus a dot v times e over c. And then I have plus mc squared times the square root of 1 minus v squared over c squared minus ea0. And then I have plus a dot v times e over c. This will cancel this one. And this expression here can be also written as mc squared over square root of 1 minus v squared over c squared times 1 minus v squared over c squared. And therefore, when you rewrite this part, which should actually be equal, so in the general case, this part here will be equal to this one. So let me rewrite it in the general case. I have to divide by the square root of 1 minus v squared over c squared. And therefore, this term will cancel this one, because when this one multiplies mc squared, I have minus mv squared. And then when I divide by this square root, I will get exactly that term with a minus sign. So the two will cancel. The two terms will cancel. And I can rewrite this as mc squared over the square root of 1 minus v squared over c squared minus e a0, like this. And for small velocities, this will be approximately equal to mc squared times 1 plus 1/2 v squared over c squared. So I have simply expanded this square root in the denominator minus e is 0. Therefore, this will be equal to approximately equal to mc squared plus 1/2 mv squared minus e a0. And now you can see that this is the classical non-relativistic kinetic energy, and this is some kind of potential energy, and this is the potential energy due to the conversion between mass and energy. So this mass here, the mass of the electron, can be converted to energy. So this is some kind of potential energy. And in classical physics, this term does not appear. So the classical non-relativistic Hamiltonian will be this part of the expression, right? So let me write it as Hc, the classical non-relativistic Hamiltonian, is simply equal to 1/2 the mass of the electron times v squared. So I can also rewrite v squared in a different manner from this expression here, because I have related the velocity and momentum. So I can rewrite that as v momentum divided by the mass plus the vector potential times E over C times M squared. So you just simply have to do the algebra there. And then I have minus E times A0. And this can be also written as 1 over 2M P plus A E over C squared minus E A0. Now, this is the Hamiltonian, the classical non-relativistic Hamiltonian for a particle in an electromagnetic field. Now, we also want to consider spin, and in particular, we have to introduce Pauli matrices if you want to talk about spin. The matrices will be denoted with this vector sigma, which contains the three components sigma 1, sigma 2, and sigma 3. Sigma 1, sigma 2, sigma 3, and each of these three components is a matrix. And the Pauli matrices, and I will show you the importance of these matrices. And in particular, we have that the commutator between sigma I and sigma j is equal to 2i sigma k times epsilon ijk. Epsilon ijk is simply the Levi-Civita symbol, and then I also have the anti-commutator between sigma I and sigma j, which is equal to twice the Kronecker delta ij. Now I want you to notice the fact that if I take the dot product between these matrices and a vector that I will call B, it is simply a generic vector, and I take the square of this vector, and so in particular this will be an operator, because this means that I have sigma 1 times B1 plus sigma 2 times B2 plus sigma 3 times B3, but B1, B2, B3 are just scalars, and sigma 1, sigma 2, sigma 3 are matrices, 2 by 2 matrices. So the result will also be a 2 by 2 matrix. Okay, so it is something that will lead us to a matrix. It's an operator. Let's rewrite this using index notation. I have sigma I, Bi, times sigma j, Bj, and this is also equal to sigma I, sigma j, Bi, Bj, and if we use symmetry, we can rewrite this as 1/2 sigma I, sigma j, plus sigma j, sigma I, Bi, Bj, but Pauli matrices are such that this commutator, and this is an anti-commutator in particular, it's exactly this expression here. This is twice the Kronecker delta ij, so here we get simply delta ij Bi Bj, which is equal to the magnitude of the vector B squared. And we should multiply this by the identity matrix, because this is an operator actually, as I said earlier, so this is not really a scalar, because on the left we really have an operator. Now, we want to generalize the expression for the Hamiltonian, and by using this fact, the fact that if I take the dot product between the Pauli matrix and the Pauli matrices and a generic vector, I get the square of the vector. So this is an important property. And I can use this property in the Hamiltonian. So let's rewrite the Hamiltonian that we found here. I will simply call it H. And I'm going to use this fact, the fact that I can also rewrite the Hamiltonian like this, by taking a dot product between the Pauli matrices and the vector P plus A E over C, and I have to square this minus E A0. So the result will also be an operator, and this is due to the fact that for an electron we have two different types of spin. So we have actually to consider spinors, and I don't want to be too technical about that, but I want to show you that from this expression here, the more general expression for the Hamiltonian, and in this case we are in quantum mechanics, we also have to consider operators, also for momentum. And now if I consider this expression, I can show you that I can also derive an expression which was postulated by Pauli, or you can say derived by Pauli, for the Hamiltonian. So let's try to rewrite this expression in a different manner. The manner that Pauli rewrote this expression is the following. So let's rewrite this parenthesis here squared. So sigma dot product B plus A E over C squared. We can rewrite this as sigma I sigma j times Pi Pj plus E squared over C squared Ai Aj plus E over C pi aj plus ai pj. And now what I want to do is I want to use operators. So in particular, I know that the commutator between pi and the aj can be written as the commutator between minus I h bar d over dxi and aj. So this is equal to this operator acting on that. So we will get minus I h bar d over dxi of aj. But we also have this operator acting on the right and aj on the left. So we have minus aj I h bar d over dxi. And then I have minus this, which acts on the left. So we get plus, because we have another minus here, plus aj I h bar d over dxi. So these two will cancel. And I can rewrite the expression here in this manner. I want to rewrite also this part, 1/2 sigma I sigma j plus sigma j sigma I times pi pj plus e squared over c squared ai aj. And I can do that because this part is symmetric with respect to the indices I and j. And then I have plus e over c sigma I sigma j times, I'm going to rewrite this term as ajpi, but I also have to add this quantity because the commutator is not zero. So I have minus I h bar daj dxi. Let me write it as plus, and then I'm going to put I in the denominator. So I divide by I. And then I also have plus ai pj. And okay, this is one expression. And then I can also rewrite it like this. Now I have delta ij from this times pi pj plus e squared over c squared ai aj plus e over c times sigma I sigma j ajpi plus sigma j sigma I. So in this case, I'm going to switch the order between these two simply because I can switch the order also here. So if I switch the order there as well, the result won't change. And here we'll have aj times pi. So it will be the same as that, this one. But these two expressions are not the same because sigma j and sigma I do not commute. And then I will also have another term that I will write here, plus e over c h bar over I sigma I sigma j daj dxi, and this is equal to b squared plus e squared over c squared a squared plus twice e over c a dot p. Why is that? Well, because I can rewrite this as anti-commutator sigma I sigma j times aj pi, right? So this will be twice delta ij, and therefore I will get that expression there. Okay, so it's quite trivial. And finally, I have the last expression here. I have plus e over c h bar over I, and I'm going to rewrite it as 1/2. And here I will rewrite sigma I sigma j as sigma I sigma j minus sigma j sigma I plus twice delta ij times daj dxi. I can do that because twice delta ij is simply equal to sigma I sigma j plus sigma j sigma I. So this term will cancel this one, and therefore sigma I sigma j plus sigma I sigma j is twice sigma I sigma j, which will cancel this factor of 2 here, and therefore I will get back my previous expression. But now this is the commutator between sigma I and sigma j, and it is equal to twice ai epsilon ijk sigma k. And finally, when I multiply epsilon ijk with the derivative aj with respect to xi, this will simply be the curl of the vector A, which is equal to the magnetic field B. So in this case, I will use B for magnetic field. Therefore, I will get this expression P. So I can put together these three, and I can rewrite them as P plus E over C times A. So these are vectors, and this is squared, plus E over C H bar, and then I will be left with sigma dot B. And finally, I can write my Hamiltonian in this form is 1 over 2m P plus E over C A squared plus E over 2mc H bar sigma dot B minus E A0. And this is the more general expression for the Hamiltonian, where I also consider spin. This term, you can see that takes into account the fact that we have spin. So the electron also has a spin, and it will influence our Hamiltonian when we take the dot product between the Pauli matrices and the magnetic field. So you can see it here. And this is the way that Pauli wrote the Hamiltonian, by taking into account a system where we also have spin, a particle with 1/2 spin, which is the electron.